All right, welcome. If I say this is machine learning in production, you're roughly in the right place. All right, I don't see a lot of people leaving. All right, thanks for coming. We're spending a semester together. I'm Christian. In this course, we're going to talk about how to build software systems that have machine learning components in them. It has a lot to do with how do we build end-user products, even though we have a model in there that might be an unreliable component? How do we do this safely? How do we do this securely? How do we build something that we can potentially sell? I think I can just go right into it. I want to start with a case study and have you discuss something in a minute. And let's talk about music generation. There's a lot of academic research, or has been for a couple of years, on generating music with LLMs or with other models, specifically. Maybe let me just show this. Has anybody played with Suno before? It's not the latest and greatest anymore, but it's one of the more popular ways of trying to commercialize this. I can try to run it, but audio doesn't work particularly well. Let's try this. What should we do a song about? Let's say ML ops and the limits of LLMs in modern applications. And what kind of music would you like to try? Jazz, Bollywood. Bollywood sounds better. Bollywood song. Any further instructions? Make it funny. Let's see whether that works. I think I came across this for the first time maybe a year ago, and that felt like the future. I guess this is now kind of old, and you have the same. So people now create entire music videos automatically generated. Let's see whether that works. I think I should have specified we want this in English. 1 second. Let's try this again. I think audio quality through this laptop setup here will be really funky. Believe me that it works. There's actually people who are quite successful with this. Apparently, this is a new TikTok trend that, not my community, but where people just go to their parents and say, hey, this is the new most popular country song. And then they play one of these AI-generated songs. Most of them are quite filthy. The explicit tag is very justified for those. So maybe don't play those kind of songs. But there's people having millions, actually millions of plays on Spotify with completely AI-generated music. This goes quite viral in places. So let's go back to this. So a couple of years ago, there was a lot of research on how to do music generation. There's LLMs that generate the lyrics, and then there's specialized models that have been trained on a lot of music, and then they need to untrain the names of artists for copyright infringement reasons. So you can't say, make it in the style of Taylor Swift, but you have to describe what you think the style of Taylor Swift is. Now, let's say you have worked on this as part of a master's or PhD degree, and maybe your research was about how to make this more energy efficient. So you published a couple of papers. These big models make this slightly more energy efficient. You got this published, 30% energy improvement. Wow, this gets you into conference, right? Maybe NeurIPS paper or engineering paper. And you keep talking to a couple of friends. You're pretty excited about this. Let's assume Suno isn't out yet. You're pretty excited about this, and you want to commercialize it. You want to build something like what is now Suno. right? You're building this, you're expecting, oh, people maybe use this for all kinds of things. And this is where I want you to think about, if you were actually gonna create this, you and two friends, maybe you build a company and hire more people over time, what kind of problems might you run into over time? And I want you to think about a few different problems. One machine engineering challenge that you will face, one engineering challenge on building the product in a way that people can use it, one challenge from operating it, so keeping it running, serving customers and updating it over time, one team and management challenge, one business challenge, and one safety or ethics challenge. Questions so far make sense? So what I want you to do is talk to the people next to you, form small groups. You have about 10 minutes, talk what you're doing and post one of each challenges as a group. All right. Let's talk about what you talked about. Bogdan has a microphone over there, and he's going to ask one of you to start, and then we can ask other people. And typically a good strategy for picking a volunteer is to look at people who look away, who avoid eye contact. All right, can we start? And if you don't want to, you can give the microphone to somebody else. Take the microphone and give it to somebody else. It's now your responsibility. Or Bogdan picks another person. Very last row is also always very inviting. So let's start with an engineering machine learning chat. No, actually, let's not. I don't really care about the machine learning challenges. We want to build products with a model, right? So let's start with an engineering challenge. What did you talk about?
We talked about how we can build the product in a fast and reliable way and how it can handle a lot of users at one time.
So really scaling it for a lot of users, right? And reliability, what kind of things are you concerned about with reliability?
Security, like how is the system secure for the users?
Okay, security. All right. One more thing. So I know most of you are master students. Are you above getting chocolate for participating in class discussions? All right. I'm going to try to throw. It's very hard for the last row. So people in the area maybe also pay attention. It's dairy-free, but not nut-free. Oh, sorry. All right. Somebody else has a different engineering challenge? Any volunteers? I have more chocolate. What did you talk about as engineering challenge? As the engineering challenge, the second point? What did you talk about? You probably wrote something down.
Yeah, I think we mostly focused on safety.
Okay.
Essentially, another issue, I think it goes maybe to safety or ethics. I think we discussed that a bit more. How the company stores and uses user data and how transparency lets its users know how their data is being stored and maintained.
So you're worried about the users upload something or have their video, their music there and how that is stored, or?
Yeah.
Okay.
Yeah.
All right. Closer. Who has a challenge for operating and updating the product? What kind of, yeah? Go ahead.
I think for operating and updating the product, it is important to define the project scope or product scope, because there are something we should prioritize first to maybe have a MVP.
Okay, so as a team, you want to think about what do you implement first, right? What do you implement first? What are the features that are the most important for releases? And you need to be able to release things without taking everything down for a week, right? Who has another challenge? Right. Right. If something goes wrong in a new version, for example, you have very explicit content, but you don't want it, right? You need a mechanism. You might be panicking, right? Somebody calls you, you're in the New York Times story for something. You want to be able to stop, and shutting down is the last resort, but maybe you can roll back to an earlier version, right? All right, a team or management challenge, somebody?
Yeah, so they mentioned it's being started by two friends, and sometimes friendships without your judgment about, your friend's abilities.
All right, your friendship might end. What does it mean for the company? Right. Any other challenges? You might need a microphone there, or shout.
I was thinking splitting up team roles, and also since assigning equity is really important in a startup very early, it's kind of also important to figure that out as well.
All right, I can't help you at all with how you split up equity in a startup, but how do you assign responsibilities, right? Who does what in a team, and does it change over time? Is it stable? Also, who does all the engineering things if all of you have a machine learning background, right? So there's questions like this. And any other management or teamwork concerns that you can foresee?
So when there's a limited cross-domain expertise among the team members,
Yep.
So that is a kind of a challenge that.
Yep, that you hire somebody who's maybe a database expert, but you really don't know how to talk to a database expert. All right, and the business challenge. Louder.
That idea of the song that we
Mm-hmm.
is it or what?
Yep. I think right now the idea is that AI generated content can't be copyrighted. So I think, at least in the US, that's a going hypothesis. But beyond the IP of the song generated, what other IP might you be worried about? And they are all getting sued, right? These companies. So what's your business model if you already know? Like, I think they're spending a lot of time on lawyers or a lot of money on lawyers, right? What are other business problems that you might expect or business challenges?
Related to this, or if a lot of studios are using PDMs or use it for their tracks, so if you give it to them, and they might produce different licenses of the.
Yeah. In general, the question, how do you make money from this, right? Do you charge users per song? Then will somebody use it? Do you charge a subscription? Are you paying more towards some cloud provider for the inference than you're actually making? Which I think is a problem for almost all of these companies. And then finally, a safety and ethics challenge. Copyright issues, yeah, and Dr. Oh.
If you're training data on common boards, which are ethical.
Yep. Are you just ripping off Taylor Swift, right? Is this ethical? I don't know. She's rich enough. She can probably. But deepfakes is another one, right? So if you kind of create. This has happened a couple of times where people pretend to create music of a certain artist that the artist didn't create, right? And how do you deal with that, right? Do you have safeguards for that? Other ethical issues? Yep. Is Visa going to stop all payments because of explicit content on your platform? You have a safety challenge. Safety generally has to do with harm. Doesn't need to be killing a person, but financial harm, reputational harm. Yeah, if you create a very personal song for a friend or so, right, if that gets leaked with your social security number in the song, I don't know. I have no idea. So what I try to do with this is give you an overview that when we're talking about building products with machine learning components in this class, this is kind of the flavor of the class. This is mostly what we're going to talk about. I don't really care much about the model. I assume somebody already knows how to build the model. Somebody has done the machine learning innovation. We will do very little kind of actual machine learning modeling in this class, but we're going to think about, assume you have a prototype of a model that maybe somewhat works pretty well. What does it take to build a product here? And I'm not a business person necessarily, so we're not going to do a business plan, but we're going to focus on the engineering challenges mostly, which includes teamwork challenges, operating challenges, safety and ethics challenges too. So how do you build this thing? How do you build it that you can update it over time, that you can roll back changes, that you can scale it, that you have a user interface that people might use, right? That you have safeguards for creating explicit content or leaking private information. And so this is kind of the flavor of this class. So if you're thinking about building this, one thing that when you're building a system you often care about is what kind of quality are we after? In the end, when we're building something, what kind of quality do we want to achieve? There's things like usability, latency, speed, things like this. What matters for a music generation product? What do we really care about? So for the model, we have certainly ideas about originality of the songs, right? They are not supposed to look all the same. But beyond the model for the product, I mean, we care about that the product as a whole, right? Our customers create original songs. What else might we care about? Free or low cost, good luck with that. If you're using a big, yep.
AI-generated content, it feel like someone just sang it right now.
Okay. You want it to sound realistic, which again is probably more of a model problem, right, than building the product around it. Sorry.
It should be available on multiple platforms as well, from mobiles or laptops.
Yep. So just building a user interface that's actually usable, right, in a broad sense, typically on web applications, maybe mobile applications. So usability, making it easy to sign up. You really care about scale and operating cost, right? So you might actually really worry about how much are you paying to OpenAI or AWS every month, and can you cover this with subscription cost? And one more comment?
Yeah, I was going to say low inference times and low latency when it comes to actually
Yeah, time is one thing, but these days we're really worried about cost, right? Inference cost, yeah. All right, and then one last question in this context. Beyond the model, what are all the non-machine learning parts that we actually need to build when we want to build the system? We have the model, and then we have all kinds of other stuff around the model. UI.
Software infrastructure, like platform, currency issues.
Yeah, all kinds of back-end issues, something like the database where we store all the songs, the infrastructure where we run all the model inference, right? What else? Testing, data collection, some sort of pipeline that we can update things automatically, right? So that's itself doesn't use machine learning, but it is used to build or deploy the machine learning model. We need to process payments, right? So I don't know, what did I show you? So what you often have is some sort of application that has all of these parts, and somewhere in all of these parts, there's a model. For some applications, the model is the essential part. If you don't have the model, there's no product, right? With music generation, without a model, what are you doing, right? It's a really essential part, but it's not the only part of the system. Sometimes it's a small part. You just worked on kind of models in Excel, Copilot kind of stuff, right, with Microsoft, and Excel still works without the models. Actually, most people, I think, don't want the models, right? So they try to add it as an add-on. The product is there, and we have the model as a small addition. It's a very different kind of building a product where a model is a small addition, whereas the model is a core central part. But in both cases, you have all this non-machine learning part in addition to the model. And often it's much more complicated than this. You have often multiple models, interactions of models. We will talk about a bunch of these things. And one more thing I wanted to get to is that in building these, we have all kinds of people with different specialties that need to work together. In this class, I'm kind of oversimplifying it for the most part and talk about data scientists and software engineers. So on the one side, you have the people who really know machine learning, often traditionally with a PhD in machine learning or really taking all the CMU machine learning classes, right? And on the other side, you have people who come from a more traditional software engineering background. You know how to build software applications without machine learning, build user interfaces. You have all the operators, system administrators knowing how to scale systems. You have also data engineers, domain specialists, business team, project managers, designers, UI experts, and so on and so on. And to really build a product, you often need lots of these people to work together. And they come from very different backgrounds. I don't want to blame one side or the other, but there's different ways of how we train those people and different ways in how these people think. The typical data scientist doesn't really care about deploying something or building a product. They're incentivized working on a fixed data set traditionally and on a benchmark. They want to get more points on that benchmark. This is how they're trained. Like if you've ever taken it, I mean, you've all taken machine learning courses, right? Think about it. You typically give them a data set and then one of two things happen. Either you implement the learning algorithm and try to get as high of an accuracy as possible, or you're using existing libraries and try to get as high accuracy as possible, right? We're typically focusing on the learning part, and there's almost never in a machine learning class where you take the model and deploy it for something in the real world, where you actually see unseen data. I mean, in an artificial setting, yes, or where data really changes over time. That's not very common. And that's not how most data scientists think. And so to them, it might be quite a jump to get out of a notebook and actually face something that they need to update once a week or more often. And on the other side, you have software engineers who are used to building products and trying to ship something, even if it's maybe not quite perfect. They're focusing much more on maybe customer satisfaction, working with an end user, scaling things, working with really large systems. They often don't understand machine learning very well. It changes a little bit these days, but traditionally there's studies when software engineers build models and it doesn't work, they have usually two things that they try, more data or deep learning. There's nobody who goes out and actually checks data quality or triages things, tries different strategies. So data scientists have their own expertise, software engineers have their own expertise. I'm not saying that one is better than the other, and they don't work well together. They are working in silos. They don't really understand each other. Like those people usually haven't heard of requirements or don't appreciate it, right? Those people have no idea how to analyze training data and look for outliers or things like this. So you expect a lot of different collaboration challenges over time. We've interviewed lots of teams also. Often the data scientists feel they're pushed to do more engineering work. They don't want to do the engineering work. They rather focus on their modeling. The engineers don't understand the data scientists or are then forced to take a notebook and pretty much throw everything away to make it actually work in production. But in doing so, they also make the models worse. There are all these kind of problems. They often work in very strict silos. So there's a data science team and a software engineering team that doesn't speak to each other. So you probably have a completely separate front-end team that may not even know much about how the model works in the background. And the model team in the background maybe at some point gets told, you really need to lower your inference time and your inference cost, but it's not usually their first priority. Their first priority is best accuracy, best songs, or something like this, right? So everything else typically comes later. So when we're hiring in these contexts, there's a lot of talk about finding these unicorns, finding people that have the computer science background, the math background, the domain expertise too, right? They're music experts or medical professionals. And these unicorns, they are called unicorns because they're kind of mythical, right? We hope that they can do everything. We want to hire them, but there's very few people like this. Like, who goes and does a PhD in data science and also in medicine and or music and also in an engineering field, right? There's just not enough human capacity in most cases. And the few people that we have that kind of bridge this engineering data science gap, they're usually very expensive to hire. And you can pay a lot of money to try to keep them happy, right? The better strategy is typically to hire multiple people that can work together in a team. And here the idea of T-shaped people is, I think, a very useful concept and something how we're thinking about this in this course. So you have I-shaped people, these are experts in one thing, like traditionally siloed, studied a PhD in data science on one specific narrow topic. You have generalists, managers, who know everything a little bit, but nothing in depth, who can connect a lot of people. And what you really want to have productive teams, it's been shown over and over again, are people who have a specialty in one field, but who are broad enough that they can talk to others in the team. So now you can hire people with multiple different specialties. They're not experts in everything, right? The data scientist is not suddenly a big database expert, but they know what question to ask and how to communicate with somebody. And that's what we're trying to do in this course. We don't have enough time to make you an expert in every single area, right? Most of you come in with an expertise in data science or software engineering. And what we're trying to do is bridge this. For example, we're doing all of distributed systems and cloud systems in like one lecture. Right? If you want to become an expert, there's an entire course on this. What we're trying to do is give you an overview, right? Talk about how the Lambda architecture works, how MapReduce works. You won't be an expert afterward, but you know enough to appreciate what somebody else cares about, and you know when to call an expert and what to ask them, right? And that's kind of how we're approaching this class. Newer buzzwords are pie-shaped people. They have 2 areas of expertise. So you might see this in recruiting sometimes, but that's about it. Does this make sense as an overview?
Hello, everyone. I'm Bogdan. Good to meet you all. Thanks for coming. Now, what makes ML building systems with ML challenging? There's roughly 3 things. One is there's no specifications in a traditional sense. So with traditional programming, you could write, say at the method level, you could write some spec for what the method does and how it does it and so on. And as a user of that method, you didn't really need to know anything else except this sort of short spec, and you could use it just fine. If you're a developer of this method, you didn't need to know anything else about the system that this method is part of. You could write an implementation for it just fine. It all sort of worked this way. So software engineering was all about modularization and separation of concerns and so on and so forth. So that's sort of been traditionally the case with traditional software. With ML components now, kind of hard to think of specifications in the same way. There isn't really one. I mean, sure, the system must, I don't know, generate a song or something. That's very high level, but it doesn't say anything about how. It doesn't say, any of the traditional things that specification contains, and it also makes it hard to test because of this. How do you know if a song is good enough? What does it even mean for a song to be good? What does it mean for it to be correct, etc. So we don't have these traditional software engineering things that made it easier to understand what code does and made it easier to test it and so on. It's more black boxes. And maybe that's okay, maybe that's justified because we're using machine learning components for problems that are harder, right? It's precisely because we cannot write a specification in a traditional sense. We cannot specify what the behavior and so on is, that we're using machine learning in the first place, right? These things are hard. So maybe that's okay, but that's something that's fundamentally different. Also, if you do specify what you want the thing to do, for example, as part of your prompt, which we often do, there's no guarantees that it will actually follow your instruction anyway. So that doesn't really work. And with agents, it's no different. So that's one. Second, it's also data focused and builds on data in ways that are different. So, for example, with a machine learning system, you train on a bunch of data, and you have a product, and you release it out into the world, and you really want to get these users using your product, because all of their data is what you train your next generation of the product on. And that's great, because then you have a V2 model that's out, which attracts even more users, and so on and so forth. You're in this sort of loop in this cycle where you're feeding data that your users have provided you with to build the next generation of your product. And you keep doing this over and over again. And that brings about lots of challenges with data pipelines, with scalability, with hardware. There's a lot of specialized hardware that you need to be able to set this up. For training, for inference, it's becoming increasingly harder for anyone to do this. Maybe there's a handful of companies that are able to do this. You've seen the news, I guess. Companies are now buying nuclear power plants to supply their data centers with enough energy to be able to even do this kind of training and inference. So there's a lot of this specialization of hardware and scalability challenges that come with this. There's also this shift from sort of deductive, math-like logic reasoning to this inducting or learning from data, generalizing from observations. That's causing scalability issues. So that's the second. These models can also make mistakes. This is a cute example where these are, I think, a bunch of goats in a tree. And this is real, right? Where is this from? But where are the actual goats? Where do you find them? Okay. Does anybody know? All right. Maybe this is identifiable. The point is that this image was miscaptioned by two models at the time. First one said a flock of birds flying in the air. The second one said a group of giraffes standing next to a tree, neither of which is correct. So ML models can make mistakes, and they can do so in unexpected ways. Perhaps these were sort of unforeseeable kinds of mistakes. And it's hard to foresee these because precisely there is no spec, like I mentioned before. You don't actually know you cannot specify what the behavior should be. So all of these questions around correctness, what does it mean for the output to be correct? We're not thinking about it in the same ways. We're thinking more about what does it mean for this to be accurate enough on average versus what does it mean for it to be correct in a traditional sense, usually on some test data. So that's another one. The big challenge here is that these models interact with the environment. So think self-driving cars, right? You have some LLM these days that is deciding how the full self-driving thing on a Tesla works. And whether or not to stop or to crash into another car or whatever else, avoid a pedestrian. Right? Maybe you have an LLM that is helping a clinician diagnose some disease, or maybe even this transcription service. Maybe the LLM is just transcribing the conversation the doctor is having with you, and maybe it's entering a wrong diagnosis for you in the patient file, things like this. So there's all kinds of harms that could come from the interaction of these systems with the world. They don't exist in a vacuum. They may influence the world out there. So we really have to think about sort of how these things have an impact on their environment. So now the point of this class, I think, is that although these are big challenges that are maybe made worse by machine learning components, they're by and large not new challenges. So it turns out that software engineering has had to deal with unreliable components for a long time, has had to deal with scalability, has had to deal with high-risk systems for a very long time. So we have all kinds of tools and techniques from these more traditional systems that share lots of commonalities with these machine learning-based systems that we will draw from in this class. Right. So the point is, ML maybe just makes these challenges more obvious, more visible, maybe intensifies them to some extent, but by and large, they're not new, is what we're claiming. So here's one sort of way to think about this. With traditional software systems, we have a lot of experience building sort of run-of-the-mill things like websites for restaurants or, I don't know, video streaming services or whatever else. And these are relatively low-risk systems that we really, maybe don't care too much about, because the worst that can happen is you can't access some website, at some point. So it's not all that bad. But while that's the case, we have also historically built very complex safety-critical systems, such as the ones that power nuclear power plants, or such as the ones that drive space exploration and so forth. And it is true that these occasionally do blow up. There's all kinds of good stories about space shuttles and so on blowing up. But by and large, over decades, the software engineering community has developed all kinds of techniques to deal with such high-risk, safety-critical scenarios. And there's a lot we can draw from that here. So if you think about this, for sort of what's happening today with machine learning components, arguably, we are building more of these sort of higher risk systems, social media and photo things and robots and smart homes and so on, self-driving, higher risk systems. But we already have lots of experience that we could draw from. It's just that we're doing more of this high risk stuff than before. It's not that we're doing something that's fundamentally different than before. Okay. So that's roughly the kinds of things you will hear us talking about over the course of the semester. We'll go in a lot of detail in all of these. All right. So the point is that we're building larger systems that have machine learning components. The focus in this class is going to be the system perspective rather than the machine learning component itself. We're going to think about the bigger system. We'll try to bridge this historical divide between data scientists and software engineers that have maybe been trained in different ways, maybe have trouble talking to one another. So there's going to be a lot of focus on teamwork and collaboration between these two sets of people. We'll highlight scenarios in which both software engineering expertise and data science expertise is important, and we will show which of these qualities are relevant beyond just model accuracy. And I guess the high-level point of the class is that there's nothing new here. Is that fair? So I think he makes this point about how all of machine learning is just requirements engineering. So, if you want to hear this contentious argument develop over the course of the semester, please come back to class. And I think that's what I have for today. So we're off. Thank you.